Practice 121. It's right after what we did yesterday. Okay, so the formula that you'll get on your test is this one. So A equals A sub 0 e to the kt. That's the formula you're going to use on 1, 2, and 3. So we're either solving for the k value or we're solving for t, most likely. You have to know how to use the formula to help you. So strontium-90 is a radioactive material, and it decays according to this equation. How nice, they gave us the K value. What is the half-life of strontium-90? So we talked about what a half-life was last class. So a half-life, if I have 1,000 grams, the half-life is how long it takes to get to 500 grams. And then another half-life gets you to 250. So you keep having, so if it's 1,000 years, this would take 1,000 years. If it's 20 years, this would take 20 years. So 121 guided practice. So they've given you the K value, but they want to know what is the half-life for strontium. You need to pick a starting value and an ending value that makes sense for a half-life. So for example, start with 1,000, end with 500. It means the starting amount at time 0. The 0 is not actually the number 0 that you're plugging in. No, and I'm going to show you why. Good question. So I'm picking 1,000 as my starting value, and then I'm ending with 500 after one half-life, right? So I've got negative 0.0244 t up here in the exponent. What if Cassidy started with 40 and ended with 20? And what if Christina started with 10 and ended with 5, and I started with 2 and ended with 1? When do you get that same ratio? Your first step is to divide A by A sub 0. Won't whatever you picked as your A divided by your starting value always come out to a half if it's a half-life problem? So it doesn't matter, it's kind of an arbitrary amount to get you to that idea of a half. So I've got a half equals e to the negative 0.0244t. What's my next step? This is an exponential equation. How do I solve for the exponent of t? Yep, so you can either, I don't know the method you've chosen, but you can change to log form, or you could take the natural log of both sides. It gets you to the same result. I'll show you both ways. If I take the natural log of a half, and then I would bring down the exponent in front. So I took the natural log of both sides. Natural log of a half on the left, natural log of e on the right. I brought down the exponent because that's the power rule. Natural log of e is just equal to 1. So you end up taking the natural log of a half and dividing by negative 0.0244. If you changed into log form, you get the same answer. If I changed into log form, it would be log base e of a half equals negative 0.0244t. So whether it's the log base e or natural log of a half, that means the same thing. And you divide by negative 0.0244. So basically, if you look what's happening, you're taking the log of the ratio, or the natural log of the ratio, and dividing by the k value. So what is the half-life? What'd you get? 28.41, yep. So that would be years. Did anyone not get that on their calculator? So it's the natural log of a half divided by negative 0.0244. Or 28.4, fine. Oh, 28.41, yeah. Okay, so that was a decay, right? So our K value was negative. Number 2, it's the same starting formula, except now K is going to be positive because this is going to be uninhibited growth this time. It's a bacteria growing. If 500 bacteria are present and there's 800 after 1 hour, how many will be present after 5 hours, and how long to reach 1,000,000 bacteria. They didn't tell me what K was. So I need to take the first part of my work using 500, 800, and 1 hour and find K first. So I'm just going to do it over here because there's kind of a lot of work. So I got to find K first. So my formula to find K is I'm ending with 800, starting with 500. I don't know K, and it took 1 hour of time. So you're going to get E by itself, change into log form, and solve for K. Yep, so your first step would be dividing by 500. So I'm just going to leave it as 8/5 equals E to the K, because K times 1 is K. Change into log form or take the natural log of both sides, gives you the same result. So the natural log of 8/5 equals K times the natural log of E, which is 1. Yeah, times 1. So it's just the natural log of 8/5, right? Am I losing anyone when I'm doing this, changing from exponential to log form or taking the log of both sides? Because that's an important step. Did you get 0.47? Okay, so I need what K is in order to solve the rest of this problem. Now that I know K, you should be able to plug in K and solve for how many are present after 5 hours and how long will it take to reach 1,000,000. So the 5-hour piece, that should be easy because you're starting with how many? 500, right? I know E, I know K, and I know T. So that should be an easy one. You're just plugging that formula into your equation. 500E to the 0.47 times 5. What'd you get? Yeah, I guess, because we wouldn't round up because that bacteria, I guess, isn't there yet. So 5,242. Mine's 0.8, but we'll just leave it at 5,242. That sounds good. So the difference for 1,000,000 is now you're solving for T. So we're more sophisticated than just guessing and checking. So you're going to put 1,000,000 on the left equals 500E to the 0.47T. So you're solving for T this time, like you solved for K over here, dividing by the 500, changing to log form, solving for T. Give people a minute to try that one. Don't say the answer yet, and we'll see in a minute what you get. Okay, I'll pause for a minute. They give you the half-life. That's T. T. And it says 10 grams are present now. How many are present in 50 years? That's like the second part of the problem. The first part of the problem is we need K for this element, right? I don't know what K is. So I'm just going to use this for, they're not giving you the A and the A sub 0. They're giving you A for like the future part of the problem. So you could start with 10 if you wanted to solve for K as well. You have to solve for K first. So if you wanted to start with 5 and 10, that's a half-life. Right, because you're going to get 0.5 on the left-hand side regardless. What is it, 1690? So you're picking an arbitrary amount over here that's exactly half of what you started with to solve for K, because they're telling you that 1,690 is the half-life. So you start by solving for K. K should come out as a really small negative number because it's dk. So 0.5 equals E to the k times 1690. When you take the natural log of both sides, yeah, you're going to divide by 1690. Natural log of e is gone. You're just going to take the natural log of a half. Yep, it's going to be scientific notation. That means you add 4 decimal places to the left. Yep, negative 0.00041. This is what it looks like on the calculator. Negative 4.1. This e to the negative 4 means 10 to the negative 4th power. You slide it 4 decimal places to the left. Okay, so now that you have k, try to solve for that next part of the problem. If you have 10 now, how much will you have in 50 years? 50 is like a drop in the bucket of this 1690. So you're going to have almost all of it still left. Right. 10? Yep. 10 is the starting amount. So A sub 0 is amount at time 0, starting amount. 10, E, your new K, and you do know T. They want to know how much is present after 50 years. We don't know little a. We want to find, or big A, we want to find this amount. They're giving you the initial, E, K, and T. T is 50. Yeah, it should be. What did you round, though? To what? 0.4? That's what I rounded to. 9.8. You didn't use a negative K value. Yes, arrow up. I think you probably got negative.
I probably did. Yeah, I did.
If it's decay, right, you did it as growth.
Yeah.
9.8 grams is pretty darn close to 10 grams, right? You've retained almost all of your solid because it's only been 50 years. Hasn't been 1,690. That would drop it to 5. Okay, the last one before we go for, oh, do I want to do this back page? Maybe not. Okay, I want to do number 4, Newton's law of cooling, to walk you through that again. And then maybe when we come back in, you might want to do a compound interest problem on the next page together. But, all right, so Newton's law, I need the law from the previous page because I don't have it memorized. So I certainly would not expect you to have it memorized. But here's Newton's law. I'm just going to lay it above here. So it's the page right before. Newton's law of cooling. U of T is the current temperature of whatever it is. Capital T, room temperature. U sub 0 is initial temperature. Capital T again. E to the KT. So all of these are given in Fahrenheit on purpose. So if everything's in Fahrenheit, you don't have to transform the degrees to Fahrenheit or Celsius. Okay, you know how to do it? So well, we're not converting. We can solve it in Fahrenheit. That's fine. A pizza is baked at 450. It's removed from the oven at 5 p.m. The room is 70 degrees. After 5 minutes, the pizza is 300 degrees. How long to take the pizza to reach 135, which is your ideal temperature for eating? So we have to solve for K first for this pizza. So currently the pizza is 300 degrees. Yeah, I don't know if the pizza is really 450 if you pull it out of a 450 oven, but we're going for that. So room temperature is 70. So you've got the current temperature, room temperature. Then there's a plus sign, parentheses. U sub 0 is the starting temperature minus T, so minus room temperature. E to the K, trying to find K. How long has it been? 5 minutes. So that is the equation. This is your current temperature, room temperature, starting temperature, 5 minutes. So we have to solve for K. The 70s don't cancel out because this 70 is multiplied, this 70 is added. So first thing I would do, what is 450 minus 70? Is that 380? So this is 380 in here. 70 I move to the other side, right? Subtract 70. So I've got 230 equals 380 e to the k times 5. Doesn't that look just like the bacteria problem now? So solve for k. It should be a negative number again because it's well, you've kind of memorized what you're taking the log of and dividing. Yeah, that's what I was saying. I mean, you've got to get down the process and not just memorize the process. You're changing into log form, so you shouldn't forget the process. Yeah, you might want to leave like one other decimal place, like negative 0.1004, just to get it more exact. I don't know if it'll affect the answer. So now you're starting at 300 and you're going down to 135. So see if you can answer the rest of that question. So now that the pizza is 300 degrees, how many more minutes until the pizza is cooled to 135? So you ended up getting 12.6, those of you that did it?